Assalamualaikum students. Students, today we are starting, this is the first lecture of the chemical bonding, right? The chemical bonding of AS level is a bit lengthy chapter, right? And chemical bonding is very important. Why it is very important? Because when you know the chemical bonding, you know the type of the bonding, you know the type of the structure, you know the type of the particle. Like, look, the particle is like if you're describing water, if you're describing sodium chloride, if you're describing diamond, you must know that it is made up of which type of particles. Now, sodium chloride is made up of ions. Copper is made up of cations and delocalized electron. Water is made up of molecule, although the molecules are made from atom, but water is represented by molecule. Sodium chloride is containing ions. Diamond is containing atoms, which are covalently bonded only. So you must know the type of particle, and this is a very important chapter. Like, they make the basis of chemistry. Like, when you describe something, you must know that you are talking about what. Like, I simply know about myself that, like if I touch my finger, they're not that hard, they're soft, right? But this shows there is no ionic bonding, they're hard solids. We may contain ions because we are good conductor of electricity. You get electric shock, you can't touch current because you are conductor. You have ions, not electrons. A metal has electrons. Like, at the end of this chapter, you must be able to explain anything in terms of particles, in terms of bonding, in terms of structure, right? So in AS, there are how many types of bonding? You can see on the screen, there's covalent, there is dative bonding, which is called coordinate covalent bonding, ionic bonding, metallic bonding, right? I'm starting with covalent bonding. Okay, my very first lecture. Now, what is covalent bonding? Look, what is covalent bonding? We are not going to define it in the O-levels way. It is electrostatic forces of attraction between shared electron and nuclei of the bonded atoms. Look, positive attract the negative, electrostatic forces of attraction between the nuclei and the shared electron. The more they are closer, the more is attraction. They would be very close. The size of the atom is small. Smaller atoms make stronger covalent bonds. All bonds, ionic, metallic, covalent, dative, whatever, smaller atoms make stronger bonds. Yes, they make stronger bonds. They're more stronger electrostatic forces. In all sharing, there are electrons that hold them together. Now, when we study covalent bonding, there are two types of structures. Simple molecules and giant molecules. What is the difference between simple molecule and giant molecule? Big molecule, giant molecule with many covalent bonds. Simple molecules. Simple molecule. Maybe I've given the structure or I'm not given here. Okay. Simple molecule. They're small molecules. Inside carbon dioxide, there's covalent. Look, inside carbon dioxide, there is covalent. But between one carbon dioxide and another carbon dioxide, there are intermolecular forces. In simple molecule, there is covalent, there is intermolecular force. There are two types of bonds. When the covalent bond will break or make, a new thing is formed. It's a chemical change. but intermolecular force is responsible for all physical properties. Intermolecular forces depend on what? On the polarity of the molecule. Polarity depends on what? Electronegativity difference in shape of molecule. So, when you want to know about the intermolecular forces properly and detail, you must know the shape. When you will know about shape, you will be able to talk about the electronegativity difference and polarity. When you will know about the polarity, you would be able to differentiate the different types of intermolecular forces. If you look at carbon dioxide, three atoms. If you look at water, three atoms. But it is liquid, it is gas. Why? Because the intermolecular forces of water are strong. But why they are strong? What is the reason behind it? Polarity, shape, right? Electronegativity differences. So we are starting. The very first topic is what? Shapes of molecule. First, we will study the shapes. Then we will study electronegativity difference and polarity. Then I will go to the intermolecular forces. Then I will talk to you about physical properties. And after simple molecule, then I will teach giant molecules and then ionic and metallic. Right? So the very first topic today that we are going to do is shapes of molecule. Before starting shapes of molecule, you will find these notes on my website, Chemistry by Zeenat, right? And topical past papers. You will get detailed information of everything, right? But you are supposed to like, subscribe, and share my channel. Okay. So starting shapes of molecule. You know what are shapes of molecule? Like how you will describe. Now how you will know that this is pyramidal, this is tetrahedral. See, right? This is tetrahedral. Huh? This is pyramidal. This is bent. Like how they are different. This is linear. Now I'm going to explain all these. For shapes, I will explain all these on a separate sheet, but I'm going to copy the notes from here, right? Because they take a lot of time to write. Then I think there's wastage of time. Once I've written, I will use them. Now, the shape of molecule is determined by valence. Look at this word. Valence, shell, electron, pair, repulsion theory. Valence shell, electron pair repulsion. Valence shell, electron pairs. The electron pairs in the valence shell. So you must, first of all, draw the dot and cross diagram. When you will draw the dot and cross, you will come to know that how many lone pairs are there, how many bond pairs are there. Right? For example, but at the same time, wait a minute. According to this theory, the repulsion between two lone pair is much more than lone pair and the bond pair, than much more than the bond pair. But what is lone pair? What is bond pair? And how we are going to relate it to the valence electron pair repulsion theory to find the shape. Look at this. You know what we are going to do. Suppose, first I want to explain you the lone pair and the bond pair, then I'm going to relate it to this. This is oxygen. Oxygen is of group 6, right? 1, 2, 3, 4, 5, 6, right? It's bonded to 2 hydrogen. Hydrogen. This is the nucleus, this is the electron pair, this is the nucleus, this is the electron pair. Now listen. This is the nucleus. If you see, this pair is a bond pair. This pair is a bond pair. These two are bond pair. These bond pairs are attracted by two nuclei. And this bond pair is attracted by two nuclei. But this pair, which is not bonded, it is called lone pair. Lone pair, right? And this is called what? Bond pair, shared pair. The lone pair is attracted by one nucleus only, but the bond pair is by two nuclei. So the bond pair is between two atoms, the two nuclei. Right? It is between two nuclei. The one is attracting here, the other is attracting here, so it experiences more nuclear attraction. When the shared pair experience more nuclear attraction, their movement is less. They're bound to two nuclei. They're not freely moving. They're not freely moving. But this lone pair is attracted by only one. Like if I am the nucleus, I'm attracting one, and there is a shared pair attracted by two nuclei. The one that is attracted by two nuclei will be having less repulsion because its movement is less. And lone pair attracted by one nucleus freely moving this way. Look, this lone pair is freely moving. This one is freely moving. So they repel more. They repel more to each other. They're moving, they're repelling each other. There's less repulsion. There's repulsion are less, and the repulsion is least. What the molecule will do to minimize repulsion? They try to keep the lone pair as far as possible. The lone pair occupy more space. When they have more space, less space is left. More space occupied by lone pair, less space occupied by bond pair. They can get closer, they repel less. So if there are more lone pair, the bonded pair are close, their angles are less. Angle is always between two bonds. Angle is always between two bonds, right? So more the number of lone pair, more is the repulsion, more space they occupy is the result. The bond pair are getting more close, their angle is smaller. They determine the shape, the angles. See in the notes what I've written? That lone pair and lone pair repulsion is more than lone pair and bond pair, and this is least. Why lone pair repel more? Look, attracted by one nucleus, so it experiences less nuclear attraction, can move more, repel more. Bond pair attracted by one nuclei, so it experiences more attraction, so they can move less, they repel less. See, I've explained the water molecule exactly the way I told you. Now, in any molecule, the lone pairs and the bond pair repel, and they try to be as far as possible to minimize repulsion. When the lone and bond pair try to be as far as possible, they want to be at maximum separation. As a result, the lone pair of electron and bond pair get some particular positions, resulting in specific angle and shape. Suppose if we take the example, now I'm going in a systematic way. Look, suppose I have a molecule. Look, I have a molecule in which there are only two bonds, there is no lone pair with the central metal atom. Like this is a central metal atom. There is one bond pair. There is another bond pair. The central atom has no lone pairs. There are just two bond pair. This is a bond pair. This is a bond pair. They are repelling each other. their repulsion is equal, they are at a maximum separation of how much? 180. Linear. Like this. See, this is what? Linear. One bond, another bond, the angle between the two bonds is what? 180. Then the central atom is having no lone pair. Now, another case. A molecule in which the central atom is bonded to 3 bonds, bond pair. Huh? There is another possibility. Out of three, if one is lone, pair, like this, out of 3, if one is bond, 2 are lone, like this. Huh? Look. If all the 3 are shared, listen. If all the 3 are shared, look at this. In these 3 shared, the maximum separation is at 120. Right? Like, look, if I have these pens, I do it. I hope you understand. These are 3. Like, if I bring them this way, they are getting closer. They are getting closer to the other 2. So the maximum separation between the 3 is at what? 120, like the sign of Mercedes. Fan. Right? So, trigonal planar. This is called what? Trigonal planar. They're all at the same plane. Right? 120, 120, 120. Now, out of these 3, if one is lone is not going to make bond if one is lone. Look at this. Now, there is this lone. I can make this. Wait a minute. If one is lone, the lone occupy more space, they repel more. To minimize repulsion, it occupies more space. They get closer and the angle is no more 120. It is what? 170. They're closer, right? Because it will occupy more space. The angle is 117 and it looks like a V, a bend, an angle. Like, you have to forget about the lone pair. The lone pair is not part of the, you can say, the angles. The angles are not related to the lone pair. The angles are always between 2 bonds. If there are 2 lone, 1 bond, would there be any angle? No, it's linear. 1 bond. See? So, if look, if it is AB2, AB2, it is what? Linear. This is what? AB3. AB3. This is what? 120, trigonal planar, 117, bent. This is we will represent it by this. AB2E. What is E? E is lone pair. E is what? Lone pair. E is lone pair. So between the 2 bonds, bond pair, the angle is what? 117. So it's what? Bent. It is bent. And if there is just 1 bond, no angle. It's linear. But no angle. Now, listen, what we did? If your molecule is AB2, linear, 180. AB2, the central atom has no lone pair. Now AB3, trigonal planar. Huh? It is what? 120. Now, if AB2E, like out of 3, 2 are bond and 1 is lone, which occupy more space. The angle is what? 117 bend. Next, 4. If it is AB4, AB3E, AB2, E2, and last AB and E3, like one bond. Now, if there are 4 bonds, now tell me, there are 4. Do you think the 4 are like this? The 4 are like this? 90, 90, 90, 90? Huh? No. They can go this way, up and down to minimize repulsion to be as far as possible. So, 4 would be how? 4 would be like this. Their maximum separation is at what? Tetrahedron. Like this. Tetrahedron. See, this angle is not 90, 109, 109, 109. All the angle, tetrahedron. Like, look, this is what? This is tetrahedron. 109, 109, 10, all the angles, 109. If out of 4, if 1 is a lone pair, what the lone pair will do? The lone pair will occupy more space. When it will occupy more space, they get closer. When they get closer, it looks like a pyramid, 109 to 107. If there are two lone, two shared, the lone occupy much more space. The two bond pair get closer, much closer. So see, if AB for the central atom A, no lone pair, the central, no lone pair, 1, 2, 3, 4, they are repelling each other equally, maximum separation, all angles. What? 109.5. Tetrahedron. Tetrahedron. Now, AB, like if there are 3 shared, look, there are 3 shared. 1 is lone, which occupy more space. Look, they are equally repelling, equal angle. But now this occupy more space, their angle would be smaller. The angle is always between bond pair. This is 109, sorry, 107. This is also 107. And it looks like a pyramid. Pyramidal. Now, if the central atom is bonded to 2 bonds in 2 lone, what the lone will do? Much repulsion, occupy more space. 1 lone pair, then 2 lone pair, and then 3 lone pair, only 1 bond. Now there are 2 bonds. When they occupy more space, they get much closer. And it is what? 104.5. Pent. V. But if there are only 1 bond, one bond, the rest is what? Lone pair. The one bond is not going to make an angle. It's just linear without any angle. So if I summarize, what we have done? If it is AB2, means what? A is bonded to just two bond pairs, 180 linear, AB3, and then AB2 and 1 is lone pair. AB3 and AB2, 1 is lone pair. Now, trigonal planar, 120. Bent, this is what? 117. Bent. A bit smaller than this. Look, from 120 to 117 because of one lone pair. But AB4, AB3, one lone pair, AB2, two lone pairs. E2. If all four are shared, tetrahedral, maximum separation at 109, tetrahedral, AB3, a lone pair, E, AB2, two lone pairs. Now, from 109.5 tetrahedral to 107 pyramidal to bent 104.5. Look, this is also bent. This is also bent. Where is the difference? There is only one lone pair. There are two lone pairs. The angle between two bond is, here it is 117, it is 104.5 because two lone pairs repel too much. Next, and your course is what? AB6. Right? AB6. First, I'm going to AB5. AB5. Like, what we are going to do? AB2, first case. AB3 and AB2E, and then AB4, AB3E, AB2E2. But in AB5, we are not going to study AB4E, AB3E2, like, no, just AB5. In AB5, they're all bond. They're all bond. Do you think they're equally repelling? Yes, they're all bonds, equally repelling. So do you think that they're going to be like this? 360 divided by 5? Not at all. How it is? They're equally repelling. I agree. They try to be as far as possible from each other, these bond pairs. So how they're going to bond? Look. This is what? AB3. Now, if one bond is above and the other bond is below, look at this. Look at this structure. This is AB5. Huh? Between these 120, above and below is what? 90. See? But between these is what? 120 and up and down. They're going to make what? 90, 90, 90. Look. You can see all these on mall view. There's a website I will share with you in the next lecture. Right? That how they actually look like. They show the mall view, show the molecule and property dimension. Right? So this is, look, this is A, 3R like this, 120, just like trigonal planar. And one is above and one is below. So what are angles? 120 and 90 degree. This is what? 120, 120, 120, but the up and below, all angles are what? 90. And if I join them, it looks like a pyramid, up and down. A pyramid by 3 up, by 3 down, trigonal by pyramidal. What is the name? Trigonal by mean two pyramid. One pyramid up, one pyramid down, and trigonal planars, trigonal by pyramidal. AB6. AB6. The only case. In AB6, look, 4 are like this. Four are like this, square planar, 90, 90, 90. Huh? One is up, one is down. One is up, one is down. Look at this. All angles. Look, this is 90, 90. You can see 90, 90, 90. The upper one is making 90. You are not going at 180. No, opposite, no. You have to go for just all 90. If I close this, one side, two side, three side, four side up, and four side down. Look, if I close this, one side down, two side down, three, and four side down. Four side down and four side up is called what? Octahedron, eight-sided. Eight-sided. Huh? It's B, no, sorry, it's A, B, and B, and B, and B. One B is up, one B is down. They're all what? 90 degree. And if I close this like this, one side, the back side, this side, and this side, 8, 4 up, 4 down, octahedron. Now look at this. Coming to this. So the shape of molecule depends on what? Number of lone pair and bond pairs. Case 1, AB2. 2 bond pair, 1 lone pair, 180, maximum separation at 180. Case 2, AB3 or AB2E. Case 3, that was case 2, sorry. Case 3, AB4, tetrahedral, trigonal pyramidal, AB2E2, bent, AB5 and AB6, trigonal bipyramidal, octahedral, 90 and 90 and 180. And now another explanation. The linear, this is lone pair, so just one bond, no angles. AB3 and AB2E, a lone pair, which occupy more space. Bent. And 2 lone pairs, right? There's just one bond. Tetrahedral, right? 3 shared, 1 lone. 2 shared and 2 lone. 3 lone and just 1 shared, no angle, because just one bond. And now AB5, look, 3 are at 120, the up and down will make 90. So 1 pyramid up, 1 pyramid down, trigonal bipyramidal. Now if I close this like, and I just join them, 4 sides up, 4 sides down, octahedral shape. Lecture, I am going to explain, to apply these cases on a molecule like this. Like now this is AB2, this is what AB3, Like I'm going to explain all these. These notes are available on my website, Chemistry by Zeenat. Don't forget to like, subscribe, and share my channel. Up till now, it's sufficient. The next lecture, you will see the application. Okay, Allah Hafiz.